4 trillion miles away, a star waits in the dark and something inside you wants to reach it. Picture this. Shrink our sun to the size of a beach ball, and the nearest star still sits 4,000 miles away, coast to coast across the United States. Our fastest rockets outrun bullets by 100 times, and even one of those would need more than 70,000 years to cross that gap. What if 70,000 years is only where this story starts? Ahead, you will see ships built from nuclear explosions, sails pushed by lasers brighter than 1,000 suns, and human bodies cooled like hibernating bears to survive the wait. If nights like this keep pulling your eyes to the sky, stay with us and hit subscribe, because this journey goes further than any of them. No ship has ever finished it. Prepare yourselves. We begin. Somewhere past the edge of everything you can see with your bare eyes, a small red star burns quietly in the dark. It is called Proxima Centauri, and it happens to be the closest star to our Sun in the entire universe. That word, closest, is misleading. Light itself, the fastest thing that exists, needs more than 4 years just to cross the gap between us and that star. Every second, light travels about 186,000 miles, enough to circle the entire Earth 7 times before you can blink. Crossing the space to Proxima Centauri takes that speed more than 4 full years without stopping, without slowing down. Let's put a number on it a different way. If you laid every mile between here and that star end to end, you would need about 25 trillion of them. Picture the distance from New York to Los Angeles, roughly 2,400 miles. Now imagine driving that trip back and forth non-stop for over 10 billion years. That is the distance we're talking about shrunk down into something almost imaginable. Here is a picture that might stick better. Shrink our entire sun down to the size of a beach ball you would bring to the pool. On that same scale, the nearest star would not sit a few feet away, or even a few miles away. It would sit about 4,000 miles from that beach ball, roughly the width of the continental United States coast to coast. One star, one beach ball, an entire country of empty space between them. Proxima Centauri is not some far corner of the galaxy either. It is our neighbour. It is the closest one there is. Every other star you have ever seen twinkling at night sits even farther away. Some of them so distant that the light hitting your eyes right now left that star before humans had invented writing. Proxima Centauri does not drift through space alone. It shares a slow gravitational dance with 2 brighter companion stars, together forming a triple system that looks, to the naked eye on a clear night, like one single glowing point. Astronomers only confirm the family connection by measuring an almost impossibly tiny shift in Proxima Centauri's position against the background sky, a wobble smaller than the width of a single hair held about 30 feet from your eye. There is one more way to feel this distance in your bones. Forget rockets, and imagine simply walking there at a steady, ordinary human pace. Scientists have actually run that calculation. Walking non-stop, never resting, would take nearly 1 billion years to cross the gap to our nearest stellar neighbour. Entire mountain ranges would rise and crumble back into dust before those footsteps ever arrived. This is the true starting line for any conversation about spaceships and other stars. Before engines, before fuel, before shielding, this single number matters most. The gap between stars was never built for machines travelling at speeds humans currently know how to reach. Our fastest machines, our proudest engineering, were designed for a solar system that feels enormous to us, and is, on this new scale, barely a rounding error. Right now, our fastest spacecraft, the machines humanity is proudest of, would take longer to reach that star than our entire species has existed on Earth. That number is so strange, so hard to believe, it deserves its own moment. Once you understand how slow our best technology really is, everything about this journey starts to look different. The race for the stars has barely left the driveway. In December of 2024, a small spacecraft called the Parker Solar Probe did something no human-made object had ever done. Diving past the Sun, pulled in by its enormous gravity, the probe reached a speed of 430,000 miles per hour. That is fast enough to fly from New York to Los Angeles in about 22 seconds. It is the fastest anything built by human hands has ever travelled. Now hold that number in your head, because it is about to feel very small. At that blistering speed, the fastest a human machine has ever gone, a trip to Proxima Centauri would still take more than 7,000 years. 7,000 years is longer than the pyramids of Egypt have existed. It is longer than writing itself has existed. A ship leaving today at the fastest speed humanity has ever reached would not arrive until long after every language currently spoken on Earth has changed beyond recognition, if it survived at all. And here is the twist. The Parker Solar Probe only reaches that speed because it is falling toward the Sun, using the Sun's own gravity like a slingshot, built for a mission that curves close to our star rather than racing away from it in a straight line. For a fairer comparison, look instead at the Voyager probes, launched in the 1970s and now the farthest human-made objects from Earth. Voyager 1 cruises through space at a steady 38,000 miles per hour. At that pace, reaching Proxima Centauri would take about 77,000 years. 77,000 years ago, humans had not yet painted the first cave art in France. They had not yet crossed into the Americas. Entire ice ages have come and gone in less time than it would take our fastest interstellar-era spacecraft to reach our nearest neighbouring star. Voyager 1 launched back in 1977, and remarkably it is still working today, still calling home across the growing silence of deep space. A radio signal from Voyager, travelling at the speed of light itself, now takes nearly a full day to reach Earth, and engineers listening for that faint whisper describe it as fainter than a birthday candle, viewed from thousands of miles away. Even so, faint as that signal is, Voyager remains many thousands of times closer to Earth than Proxima Centauri, a humbling reminder of exactly how much emptiness still separates us from any other star. This is the uncomfortable truth sitting underneath every science fiction movie you have ever watched. The starships gliding across the screen, crossing galaxies in a weekend, are not exaggerating a little. They're exaggerating by a number so large it barely fits in a sentence. Real rockets, built with real fuel and real engines, are almost laughably slow on the scale that interstellar distance demands. So why can't we just build a faster version of what we already have? Strap on bigger engines, pack in more fuel, and push harder. It sounds simple. Anyone who has ever pushed a shopping cart knows that more force means more speed. Rockets should work the same way. They do not. And the reason why is not really about engineering. It is about math, and a particular piece of math that has been quietly ruining rocket dreams since the very first days of spaceflight. That math is where the next problem begins, and it turns out to be one of the cruelest traps in all of engineering. Picture yourself trying to throw a rock as far as possible. Now imagine someone hands you a second rock and tells you to carry it with you while you throw the first one. Suddenly you are slower, clumsier, and your throw does not go nearly as far. Now imagine they hand you 100 more rocks. This, in a strange way, is the exact problem facing anyone who wants to build a spaceship fast enough to reach another star. A rocket accelerates by throwing mass out the back at high speed. Simple enough. Want to go faster? Throw out more mass, or throw it out faster, or both. That means more fuel. But fuel has weight, and weight is the enemy of speed. To carry more fuel, you need a bigger tank. A bigger tank needs a bigger rocket to lift it. That bigger rocket needs even more fuel just to carry the fuel it is already carrying. Round and round it goes. Picture an old legend about a chessboard and a single grain of rice. Place one grain on the first square, then double it on the next, then double that amount again on the square after that. By the time you reach the final square, the rice piled on the board outweighs a mountain. Rocket fuel behaves in a similar spirit. Push for a little more speed, and the fuel requirement does not creep upward gently. It compounds, square after square, until the numbers stop looking like anything a launch pad could ever hold. Engineers have a name for this brutal cycle, and it traces back to a Russian schoolteacher named Konstantin Tsiolkovsky, who worked out the mathematics of rocket flight more than a century ago while barely leaving his small house in the countryside. His equation is often called simply the rocket equation, and it describes exactly why speed in space is so punishingly expensive. Every additional bit of velocity you want costs you an exponential amount of extra fuel, growing dramatically, brutally larger with each added mile per second. Here is what that looks like in practice. To reach even a modest fraction of the speed needed to cross interstellar space in a human lifetime, using ordinary rocket fuel, you would need a rocket so large that its fuel tanks alone would dwarf entire skyscrapers. Multiply that fuel requirement by the distance to another star, and the numbers stop making any physical sense at all. You could use every scrap of fuel humanity has ever produced and still fall absurdly short. This is why simply scaling up existing rockets, building a bigger version of the machines that carried astronauts to the moon, will never work for interstellar travel. The wall standing in the way is built directly into the physics of chemical propulsion itself, and no amount of trying harder or spending more money can tear it down. Which means if humanity is ever going to reach another star, someone has to throw out the old rulebook entirely. New sources of power, new ways of pushing a spacecraft forward. Ideas strange enough that for most of history they only existed in the pages of science fiction. Some of those ideas exist already, tested in laboratories and studied by real engineers for decades. One of them involves detonating nuclear bombs behind a spacecraft on purpose, again and again, riding the shockwaves like a surfer catching wave after wave. It sounds like fiction. It was designed for real, and some of the smartest minds of the 20th century believed it might actually work. Every engine humanity has ever strapped to a rocket, from the first fireworks in ancient China to the engines that carried astronauts to the moon, runs on the same basic idea. Burn a fuel, create hot expanding gas, and shoot that gas out the back as fast as possible. The faster the exhaust leaves the engine, the more efficient the rocket becomes. Chemical rockets, the kind that power almost every launch in history, hit a hard ceiling here. The chemical reactions that burn rocket fuel can only release so much energy, no matter how clever the mixture. That limits exhaust speed to roughly 3 miles per second, an impressive number on Earth and a laughably small one against the scale of interstellar space. Think of it like trying to cross an ocean by paddling a canoe. Paddle harder, paddle with better technique, and you might shave a few hours off the trip. You're never crossing that ocean before your food runs out, no matter how skilled a paddler you become. The tool itself has a ceiling built into it. The Saturn V rocket, the towering machine that launched humans toward the moon, remains one of the most powerful machines ever built by human hands. Fully loaded, it weighed about 6 million pounds, and nearly all of that weight was fuel, burned away within the first few minutes just to escape Earth's gravity. It could send astronauts across roughly 240,000 miles of space in about 3 days. Impressive and utterly meaningless against a target 25 trillion miles away. At that same relative speed, the trip to Proxima Centauri would stretch out for hundreds of thousands of years. Even swapping in a more efficient chemical mixture barely moves the needle. Engineers have tested nearly every combination of fuel and oxidizer imaginable, and none of them break past that same fundamental ceiling. It is baked into the chemistry itself, into how tightly atoms bond and how much energy gets released when those bonds break apart. The fastest human beings have ever personally travelled came during the return trip from the moon, when astronauts inside a small capsule reached almost 25,000 miles per hour as gravity pulled them back toward Earth. That number still stands as a human speed record today, decades later. Against the true scale of interstellar distance, though, even that blistering record-breaking speed barely counts as a first step. So chemical rockets are wonderful at one very specific job: punching through Earth's atmosphere, fighting against gravity for a few violent minutes, and delivering a payload into orbit. Beyond that, in the open emptiness of deep space, they become almost useless for a journey measured in trillions of miles. This forced engineers decades ago to start looking somewhere else entirely for propulsion, past bigger versions of the same idea toward fundamentally different ways of pushing a spacecraft forward? One answer came from an unlikely direction, a technology already quietly running on spacecraft today, one that trades raw power for something rocket scientists rarely get to enjoy: patience. That technology moves painfully slowly compared to a rocket launch, yet given enough time, enough years of constant gentle pushing, it can reach speeds that chemical rockets can only dream about. The catch, as always, is time. And time, on the scale of a journey to another star, is the one thing that keeps running out. Imagine pushing a shopping cart with one steady finger, applied for hour after hour, day after day, for years without stopping. That gentle, relentless push describes how an ion engine works, and it represents one of the strangest and most promising ideas in modern propulsion. Instead of burning fuel in a violent chemical reaction, an ion engine takes a gas, usually a heavy element like xenon, and strips away electrons from its atoms using electricity. This creates charged particles called ions. Powerful electric fields then fling those ions out the back of the engine at extraordinary speed, far faster than any chemical rocket could manage. The catch is thrust. An ion engine produces a push so gentle you could hold back the entire spacecraft with a single hand. The American Space Agency's most advanced ion engine, tested for future missions, produces roughly the same force as the weight of a single sheet of paper resting in your palm. It sounds almost like a joke compared to the roaring violence of a rocket launch. Here is where the magic happens, though. A chemical rocket burns for a few minutes and then goes silent, coasting the rest of the way. An ion engine can run continuously for years, quietly building speed the entire time. Given enough time, that tiny patient push adds up to genuinely impressive velocity, faster in some cases than what a chemical rocket ever achieves. Spacecraft using this technology have already flown successfully, visiting asteroids and testing the concept for future missions to deep space. One probe spent years orbiting 2 different dwarf worlds in the asteroid belt, sipping fuel so slowly that its entire mission ran on less propellant than a single fill-up of a car's gas tank. The engines exhaust ions at speeds exceeding 90,000 miles per hour, dramatically more efficient than chemical fuel per pound carried aboard the ship. Watching one ignite looks almost anticlimactic in photographs, a faint blue glow rather than a violent burst of orange flame, yet that quiet glow can outlast any chemical engine ever built. Could ion engines alone finish the job for a trip to another star? Do the math, and the painful truth appears. Even accelerating continuously for decades, an ion-powered spacecraft would still only reach a small fraction of the speed needed to cross interstellar distances within a human lifetime. The engines are remarkably efficient. They are simply not powerful enough, even given all the patience in the world, to close a gap measured in trillions of miles. Give an ion engine an entire human lifetime to push against a spacecraft, and it might reach a top speed still measured in mere tens of thousands of miles per hour, a fraction of what a serious interstellar mission would demand. It is a bit like training for years to become an excellent long-distance walker, only to discover the destination is on the other side of an ocean. Skill and patience alone cannot solve a problem of that scale. You need something with real teeth behind it, something violent enough to punch through the energy requirements that chemistry and gentle electric fields simply cannot touch. Which leads to one of the strangest chapters in the entire history of rocket science, a moment when engineers looked at the most destructive technology humanity had ever created and asked a genuinely unsettling question. What if, instead of fearing a nuclear explosion, you built a spaceship designed to ride one? In a secret laboratory during the late 1950s, a small group of physicists sketched out one of the boldest and strangest spacecraft designs in history. They called it Project Orion, and the idea at its heart still sounds almost too extreme to be real. Build a massive pusher plate on the back of a spacecraft, then detonate small nuclear bombs behind it, one after another, and let each blast slam into the plate and shove the entire ship forward. Picture surfing, except instead of ocean waves, you're riding the shockwave of a nuclear explosion, over and over, thousands of times, each one pushing you a little faster. Between the bomb and the ship, massive shock absorbers would soften the blow enough for a human crew to survive the ride without being crushed. The strangest part of this story is that engineers actually tested a small version of it, using ordinary chemical explosives instead of nuclear ones. A model roughly the size of a beach ball packed with a series of timed explosive charges genuinely flew through the air above a desert testing ground, hopping upward on each small blast exactly as the mathematics predicted. Seeing that little model bounce skyward convinced the team their strange idea had real merit beyond theory scribbled on a chalkboard. The physicist Freeman Dyson, one of the most brilliant scientific minds of the 20th century, worked on this project early in his career and later admitted the design genuinely could have worked. Calculations suggested a ship using this method could reach speeds far beyond anything chemical rockets or ion engines could manage, potentially fast enough to make interstellar journeys plausible within a human lifetime, at least for probes if not full crews. There was, unsurprisingly, a serious problem. Detonating nuclear bombs, even small ones, releases dangerous radiation. Launching a ship like this from the surface of Earth would have meant setting off dozens of nuclear explosions in the atmosphere, spreading fallout across the planet before the ship even left the solar system's inner neighbourhood. In 1963, an international treaty banned nuclear explosions in the atmosphere, in space, and underwater. Project Orion, dependent entirely on doing exactly that, was effectively dead before it truly began. The idea did not disappear so much as evolve. Engineers realised the underlying concept, using nuclear energy to violently push a spacecraft forward, remained sound even if bombs themselves were off the table. What if, instead of crude explosions, you used controlled nuclear fusion, the same reaction that powers the sun, and released that energy in careful, engineered pulses rather than uncontrolled blasts? This shift in thinking led directly to one of the most detailed and respected interstellar spacecraft designs ever produced, a study so thorough that scientists still reference it decades later. It imagined a ship powered by tiny controlled fusion reactions instead of crude bombs, thousands of them per second, each one a miniature star ignited and extinguished in an instant, driving a spacecraft toward another star system entirely. That design remains, to this day, one of humanity's most serious attempts to put real numbers behind a starship. It came remarkably close to solving the propulsion half of the problem. What it revealed instead was an entirely different obstacle, one buried in the fuel itself, waiting to derail the entire mission before it could even leave the launch pad. Between 1973 and 1978, a team of engineers working for the British Interplanetary Society produced what remains the most detailed engineering study of a starship ever completed. They called it Project Daedalus, named after the mythical craftsman who built wings to escape captivity. The team's goal was audacious: design a real, physically possible spacecraft capable of reaching another star system within 50 years, using only technology that could reasonably be developed in the near future. What they produced was staggering. A two-stage spacecraft weighing 54,000 tons at launch, roughly the mass of an aircraft carrier, powered entirely by nuclear fusion. Tiny pellets made of deuterium and a rare form of helium would be dropped into a reaction chamber and ignited by powerful electron beams, thousands of times every second, each ignition acting like a miniature star exploding and pushing the ship forward. The first stage would burn for 2 years, accelerating the ship to over 7% of the speed of light. Then it would detach and fall away, and the second stage would ignite, burning for nearly 2 more years and pushing the ship all the way up to about 12% of the speed of light. At that staggering velocity, roughly 36,000 miles every single second, the ship would coast silently the rest of the way, aimed at a red dwarf star called Barnard's Star, about 6 light-years from Earth. 12% of light speed sounds abstract until you compare it to anything humans have ever built. It is roughly 1,000 times faster than the Parker Solar Probe at its record-breaking peak. At that speed, the entire 50-year journey to Barnard's star would fit inside a single human lifetime, something no other realistic design had achieved before or has fully matched since. Moving that fast comes with a strange cost of its own. The design carried no way to slow down, so upon arrival, the ship and its cluster of small robotic probes would scream past Barnard's star in a matter of hours, cameras and sensors capturing everything they could during that brief, blazing flyby before racing onward into the emptiness beyond, never to return or stop again. There was, of course, a catch, and it was enormous. The design required about 30,000 tons of a rare form of helium as fuel, a substance almost non-existent on Earth. The Daedalus team's solution was almost as audacious as the ship itself. Mine it from the atmosphere of Jupiter, using massive floating factories that would spend years scooping up the giant planet's clouds and refining out the rare fuel one molecule at a time. Building that mining infrastructure alone would represent one of the largest engineering projects in human history, dwarfing anything humanity has attempted so far, and that is before a single piece of the actual Starship gets built. The fusion engine, the ship's hull, the systems needed to keep it running flawlessly for decades in the crushing emptiness of space. All of it remained years or decades beyond anything humanity could construct at the time the study was written. Daedalus proved something important nonetheless. Reaching another star within a human lifetime was not fantasy. It was physics, engineering, and enormous, almost unimaginable scale. The blueprint existed. What remained missing was everything needed to actually build it, starting with a fuel source that barely exists anywhere near Earth at all. Helium comes in more than one form. The helium filling a birthday balloon is common, cheap, and completely useless for a fusion-powered starship. The version needed for something like the Daedalus design is a rarer cousin, a lighter form of helium that barely exists naturally on Earth at all. Our planet's atmosphere and crust contain only faint traces of it, nowhere near enough to fuel even one interstellar mission. Jupiter tells a very different story. The largest planet in our solar system is a swirling ocean of hydrogen and helium, and within that atmosphere, the rare fuel needed for advanced fusion reactors exists in genuinely useful quantities. Suddenly, the missing ingredient for humanity's most ambitious starship design is not on Earth at all. It is floating in the clouds of a gas giant 400 million miles away. This creates a strange kind of treasure hunt, one that plays out entirely in the freezing, crushing atmosphere of a planet that could swallow more than 1,000 Earths inside itself. Engineers who studied this problem imagined enormous floating factories, essentially airships built to survive Jupiter's extreme pressure and cold, slowly scooping in vast quantities of atmosphere and separating out the rare helium molecule by molecule. Building even one such factory would already push the limits of engineering. Building enough of them to gather 30,000 tons of fuel, enough to launch a single starship, would require decades of continuous operation, an entire industrial supply chain built hundreds of millions of miles from Earth, centered entirely around Jupiter itself. Jupiter does not make this easy either. The giant planet is wrapped in the most intense radiation belts anywhere in the solar system, a churning storm of charged particles trapped by its enormous magnetic field, powerful enough to fry unshielded electronics within hours. Any mining operation stationed there would need shielding heavy enough to survive conditions far harsher than anything encountered near Earth, adding yet another layer of cost and difficulty on top of an already staggering engineering project. And that is only the mining half of the problem. Once collected, the fuel would need to be transported back across the solar system, refined further, and loaded into the spacecraft without losing a dangerous amount along the way. Every step of that chain, from cloud to reactor, represents a project on the scale of building an entire new branch of human civilization, dedicated to nothing but fuel collection. This is the uncomfortable truth hiding behind many bold interstellar spacecraft designs. The physics might work on paper, the fuel might theoretically exist somewhere in the solar system. Getting from theory to an actual tank of usable fuel sitting inside a working spacecraft engine requires infrastructure. Humanity has never attempted to build, spread across distances that dwarf anything in our current industrial reach. Faced with a challenge this enormous, some scientists began asking a different question entirely. What if the real obstacle was choosing the wrong kind of fuel altogether, rather than simply failing to gather enough of it? What if there existed a substance so powerful that a single gram, small enough to rest on a fingertip, contained more usable energy than entire mountains of ordinary rocket fuel combined? That substance exists. Physicists have created tiny amounts of it in laboratories. It just happens to be, gram for gram, the single most expensive material ever produced by human beings, and building enough of it for a starship might be the hardest engineering challenge yet. Deep inside a massive particle physics laboratory in Europe, scientists occasionally manage something that sounds like pure science fiction. They create antimatter, a substance that is, in almost every way, the mirror opposite of ordinary matter. Every particle of regular matter has an antimatter twin, identical in mass but opposite in charge. And when matter meets antimatter, something extraordinary happens. Both particles vanish completely, converting their entire mass directly into pure energy. This matters enormously for spaceship design because of how efficient that conversion really is. Nuclear fusion, the reaction powering stars in the proposed Daedalus starship, converts less than 1% of its fuel's mass into usable energy. Matter and antimatter annihilation converts all of it, 100%, every single atom transformed entirely into energy with nothing wasted. Gram for gram, antimatter contains more usable energy than any other fuel humans have ever imagined using. A spacecraft powered by antimatter could theoretically reach speeds far beyond what fusion engines like Daedalus could manage, potentially cutting travel times to nearby stars down from decades to something dramatically shorter. On paper, antimatter looks like the perfect solution to nearly every propulsion problem discussed so far. Reality intrudes almost immediately. Antimatter does not exist naturally anywhere on Earth, or really anywhere convenient in the universe that we could easily reach. Every particle of it used in laboratories has to be manufactured, one tiny piece at a time, inside massive and extraordinarily expensive particle accelerators. The process is agonizingly inefficient, consuming enormous amounts of electricity to produce a quantity of antimatter so small it can only be measured in individual atoms. To put this in perspective, producing just 1 gram of antimatter, roughly the mass of a paperclip using current technology, would take many years of continuous production at every antimatter facility on the planet combined, and would cost more money than most national economies generate in that same span of time. Scientists have managed to trap tiny wisps of antihydrogen atoms for a matter of minutes at a time, a genuine milestone in physics, and yet the total amount of antimatter ever produced by humanity across every laboratory and every experiment in history would still be far too small to see with the naked eye. It remains, without exaggeration, the most expensive material ever created by human beings. There is also the small matter of storage. Antimatter annihilates instantly on contact with ordinary matter, which means it cannot simply be placed in a normal fuel tank. Scientists currently trap tiny amounts using powerful magnetic fields, suspending charged antimatter particles in a vacuum so they never touch the container walls. Storing enough antimatter to power an actual starship, keeping it safely contained for years during a long voyage, remains a challenge nobody has solved, even in theory. So antimatter sits in an unusual position among propulsion ideas. Unlike faster-than-light travel, which physics itself forbids, antimatter propulsion is blocked entirely by production and engineering. by humanity's current inability to manufacture and safely store enough of this extraordinary substance, somewhere between a distant future breakthrough and complete fantasy, antimatter propulsion waits. Faced with that uncertainty, some scientists turn the entire problem inside out. Instead of trying to carry fuel on board the spacecraft at all, what if you left the power source behind on Earth and simply pushed the ship from a distance, using nothing but light itself? In April of 2016, a group of scientists and billionaires stood in front of cameras in New York City and announced one of the most audacious spaceflight concepts ever proposed. Funded by the internet investor Yuri Milner and publicly supported by the physicist Stephen Hawking, the project became known as Breakthrough Starshot, and its core idea sounds almost too simple to work. Instead of carrying fuel on board a spacecraft at all, push it from behind using an enormous array of lasers stationed on Earth. Here is the concept in plain terms. Build a spacecraft so small and light it weighs about as much as a smartphone, and attach it to an ultra-thin sail only a few yards wide, similar in principle to how wind fills a sailboat's canvas, except this sail catches photons of light instead of moving air. Engineers nickname the tiny probe itself a Starship, a sliver of a spacecraft packed with a camera, a power source, and a radio transmitter, all squeezed onto something roughly the size of a postage stamp. Then aim a massive ground-based array of lasers, potentially generating up to 100 billion watts of combined power, directly at that sail for just a few minutes. The physics genuinely works. Light carries momentum, even though it has no mass, and a powerful enough beam striking a large enough sail can accelerate a tiny spacecraft to incredible speeds in a remarkably short amount of time. Engineers behind the project calculated that a probe pushed this way could reach roughly 20% of the speed of light, fast enough to reach Proxima Centauri in about 20 years rather than tens of thousands. Some of the most respected scientists on the planet lent their names to the announcement, a signal that this idea, however wild it sounded, deserved to be taken seriously rather than dismissed as fantasy. 20 years. After chapters of numbers stretching into the tens of thousands, that figure feels almost shockingly small, almost within reach of a single human lifetime spent waiting for results. The project has faced real challenges since its dramatic announcement. Building a laser array of that scale, precisely focusing a beam of that power across vast distances without it spreading out and losing strength, remains an enormous engineering hurdle. As of recent years, the project has been placed on hold, paused while researchers work to solve the hardest remaining technical problems and build support for the next phase, though scientists involved insist the core physics behind it remains sound and worth pursuing. There is also a much deeper limitation hiding inside this idea, one that becomes obvious the moment you start imagining something bigger than a smartphone riding that laser beam. The entire concept only works because the spacecraft is almost impossibly light. Every additional gram of mass makes the ship dramatically harder to accelerate, requiring exponentially more laser power to reach the same speed. A tiny probe carrying a camera and a few sensors is one thing. A spacecraft carrying air, food, water, radiation shielding, and an actual human crew is an entirely different scale of problem, heavier by a factor of millions. Scaling this elegant, light-powered concept up to something that could carry a person turns out to be far harder than it first appears, and the reasons why reveal one of the deepest challenges in the entire pursuit of interstellar travel. A smartphone-sized probe riding a beam of light toward the stars sounds almost achievable. A human being riding that same beam does not. The difference between those two scenarios is not a small technical gap. It is a canyon, and understanding why reveals one of the harshest truths about interstellar travel. Consider what a human crew actually needs to survive years or decades in deep space. Breathable air and the systems to keep recycling it. Water and machines to purify it endlessly without failure. Food, grown or stored in enough quantity to last the entire journey. Radiation shielding thick enough to protect fragile human cells from the endless bombardment of deep space particles. living quarters large enough that people do not lose their minds trapped inside a metal box for years on end. None of this weighs a few grams. All of it, combined, weighs an enormous amount. Where the Starship probe imagined by Breakthrough Starshot weighs about as much as a smartphone, a spacecraft carrying even a small human crew, along with everything needed to keep them breathing, fed, and safe, would weigh closer to a loaded school bus, a jump in mass so large it barely belongs on the same chart. Here is where the laser sail concept runs into serious trouble. The amount of force needed to accelerate an object to a meaningful fraction of light speed scales directly with that object's mass. Double the mass, and you need roughly double the laser power to reach the same final speed, assuming the same acceleration time. A smartphone-sized probe might need a laser array producing around 100 billion watts. A spacecraft heavy enough to carry a human crew, complete with life support and shielding, could weigh many thousands of times more than that tiny probe. Do the math, and the laser power required to launch a crewed vessel the same way starts to approach numbers that dwarf the total electricity production of the entire planet Earth. Not a large power plant, not a large country's entire energy grid. Something closer to every power source humanity currently operates, combined, focused entirely into a single beam for the sole purpose of launching one spacecraft. There is a cruel twist buried inside this problem too. A heavier spacecraft needs more laser power to reach the same speed, and it also accelerates more slowly under that same force, meaning the beam has to stay focused and precisely aimed for a much longer stretch of time, tracking a target moving away at increasing speed across a growing distance. Every added ton of human survival equipment makes an already impossible engineering challenge measurably worse. Better lasers or better sail materials will not fix this. It is a fundamental mismatch between the physics of light propulsion and the physical requirements of keeping a human body alive. Light sails excel at moving objects so light they barely qualify as objects at all. Humans, stubbornly, require an enormous support system just to survive, and that support system is exactly what light sail propulsion struggles hardest to move. So if pushing a crewed ship with light seems nearly impossible, what happens if engineers stopped worrying about practicality entirely and asked a purely theoretical question instead? Forget the engineering for a moment. If you had unlimited resources, unlimited power, and unlimited time, could you actually scale this idea up far enough to work? Let's play out that thought experiment fully. Forget budgets, forget politics, forget every practical limitation currently holding back the laser sail concept. Suppose humanity decided with total commitment to build the largest laser array physically possible and use it to launch a spacecraft large enough to carry a human crew toward another star. The first problem is simply gathering that much power. Generating a laser beam strong enough to accelerate a crewed spacecraft to a meaningful fraction of light speed, within a reasonable acceleration window, would require an amount of electricity comparable to what the entire planet currently produces, sustained continuously for months or years without interruption. Every power plant on Earth, every dam, every reactor, every solar farm working together toward a single beam might come close, assuming none of that energy was needed for anything else humans currently rely on to survive. The second problem is size. To keep a laser beam focused tightly enough across millions or billions of miles of empty space, the mirrors and lenses used to shape it would need to span distances measured in miles themselves. Essentially an optical instrument the size of a small country, built with precision fine enough to focus light across a gap wider than anything humans have ever tried to aim anything across before. The third problem, quieter but just as serious, is heat. Concentrating that much energy into a beam generates enormous waste heat at the source. Cooling systems for an array producing that much power would themselves represent one of the largest engineering projects ever attempted. An infrastructure challenge layered directly on top of an already impossible power generation challenge. Picture trying to keep a stovetop burner from melting while turning up its heat output by a factor of millions. Then imagine doing that continuously for months without a single moment to let the system rest. Even if every one of these problems was somehow solved, a fourth issue waits at the very end: slowing down. A ship pushed to a significant fraction of light speed by a laser on Earth has no way to decelerate once it arrives at its destination, unless it carries its own separate braking system, adding yet more mass, which increases the launch power needed, which increases the size of the laser array, which increases the cooling requirements, each problem feeding directly back into the last. Here is the honest verdict on scaling up light-powered propulsion for a human crew. Photons genuinely do carry momentum. Lasers genuinely can push a sail. Real physics backs the whole concept, unlike faster-than-light travel, which the laws of the universe forbid outright. The trouble here is purely one of scale, so enormous that it currently sits somewhere beyond the edge of anything resembling realistic engineering, even generously imagined decades or centuries into the future. And even if humanity somehow solved every one of these problems, built the laser, gathered the power, focused the beam, and figured out how to slow the ship down safely at the other end, one final obstacle would still remain, and this one cannot be engineered around no matter how much money or ambition gets thrown at it. It is written directly into the structure of the universe itself, discovered by a patent clerk in Switzerland more than a century ago, and it applies to every single spacecraft design covered so far. In 1905, a young patent clerk in Switzerland named Albert Einstein published an idea that would eventually reshape everything humans understood about speed, space, and time. He was not a famous professor working at a prestigious university. He was an unknown clerk reviewing patent applications in his spare hours, quietly working out some of the most important physics ever discovered. Buried inside his theory of relativity sits one of the strangest and most unbreakable rules in the entire universe. Nothing with mass can ever reach the speed of light, no matter how advanced the engines, how much fuel gets packed aboard, or how far future technology someday advances. Here is the strange part of why. As an object made of matter, anything with actual mass speeds up and approaches the speed of light. Something bizarre happens to its effective mass from an outside observer's perspective. It behaves as though it grows heavier, harder and harder to accelerate further, even though its physical size never changes, as if space itself starts pushing back against continued speed increases. Picture pedaling a bicycle up a hill that gets steeper the faster you go. At normal speeds, pedaling harder makes you go faster in the way you would expect. As your speed climbs closer and closer to some invisible ceiling, that same amount of pedaling effort produces smaller and smaller gains in actual speed. Push infinitely hard, and you approach that ceiling, but according to the mathematics, you can never fully arrive at it. The math behind this is exact, falling directly out of the equations describing how energy, mass, and speed relate to each other. Equations tested and confirmed repeatedly for over a century using particle accelerators, satellites, and precise atomic clocks. Physicists have accelerated tiny particles to more than 99% of light speed inside massive underground accelerators built specifically to study this exact limit. Tunnels miles long buried deep underground, ringed with magnets powerful enough to bend a beam of matter into a circle. Every single test confirms the same unbreakable pattern. Getting closer to light speed cost more and more energy, with the final sliver of that gap requiring mathematically an infinite amount of energy to fully close. This puts a hard limit on absolutely everything discussed so far. Fusion rockets, laser sails, even wildly theoretical antimatter engines, all of them share this same universal ceiling. None of them can ever reach light speed itself. The best any of them could realistically hope for is getting close, perhaps 20%, perhaps even 50% of that speed under extremely optimistic and currently unrealistic assumptions, but never touching the true ceiling itself. This might sound like the moment the entire dream of interstellar travel collapses completely. It does not. and the reason why is one of the strangest gifts hidden inside Einstein's equations. That same theory which slams the door shut on reaching light speed also quietly opens a completely different door, one that changes what a journey to another star could actually mean for the people aboard the ship. Because speed does something else entirely once you push it high enough. It bends the flow of time itself, and for anyone travelling fast enough, the years passing outside the ship and the years passing inside it stop matching up completely. Imagine two twins, identical in every way, standing together on a launch pad. One climbs aboard a spacecraft capable of reaching a significant fraction of the speed of light and heads off toward a distant star. The other stays behind on Earth, living an ordinary life, watching the sky and waiting. Years later, the ship returns. The twin who travelled steps out, and something impossible has happened. That twin has aged noticeably less than the sibling who stayed behind. This is a genuine, measured, thoroughly tested consequence of Einstein's theory of relativity, known among physicists as the twin paradox, even though there is nothing paradoxical about it once you understand what is really happening. Time itself does not flow at a fixed, universal rate for everyone. It flows differently depending on how fast you're moving relative to someone else. The faster an object travels, the slower time passes for whoever is aboard it, at least from the perspective of someone watching from a slower reference point. This effect, called time dilation, has been measured directly using atomic clocks flown on airplanes and satellites, clocks precise enough to detect differences measured in billionths of a second. Navigation satellites orbiting Earth right now actually have to correct for this effect every single day, adjusting their onboard clocks slightly to stay in sync with clocks on the ground, or every map and location signal on the planet would slowly drift out of alignment. Every single test confirms the same strange truth. Speed genuinely does bend time. At the speeds achievable by something like the Daedalus fusion starship, roughly 12% of light speed, this effect exists but remains fairly small, shaving perhaps 1% or 2% off the crew's experienced travel time compared to people watching from Earth. Push a hypothetical spacecraft up toward 50 or 70% of light speed, however, and the effect grows dramatically. A crew travelling at those extreme speeds might experience a journey lasting only a handful of years, while decades or even centuries pass for everyone they left behind on Earth. This creates a genuinely strange emotional weight buried inside any serious interstellar mission. A crew departing Earth would essentially be saying goodbye to family, to friends, and potentially to the entire world they knew. By the time they returned, assuming they ever did, the Earth waiting for them could belong to a completely different era, filled with descendants of the people they left behind, technology transformed beyond recognition, an entire civilization that moved on without them. For a one-way journey to a new star system, this cuts differently. The crew arriving at their destination would step out of their ship younger, in a sense, than the version of Earth's timeline running in parallel back home. They would carry with them a small, frozen slice of the era they departed from, planting it on a world light years away, while Earth itself continued marching forward through its own history without them. Time dilation offers a strange kind of hope tucked inside an otherwise brutal physics problem. It does not shrink the distance to another star. It does something almost as valuable. For the people actually aboard the ship, willing to accept everything they are leaving behind forever, it can shrink the subjective length of the journey itself. The catch, as always in this story, is that reaching speeds high enough for this effect to matter brings its own catastrophic energy price tag, vast enough to make every propulsion problem covered so far look almost trivial by comparison. Here is a number that tends to stop people cold the first time they hear it explained properly. To accelerate a spacecraft with the mass of, say, a small passenger jet up to just 10% of the speed of light, using perfectly efficient engines with zero energy wasted, would require more energy than humanity's entire civilization currently produces in several years combined. That staggering total buys only 10% of light speed, a small fraction of the way toward a ceiling that can never actually be reached. This is the brutal cost hiding behind Einstein's equations, the flip side of the speed limit discussed earlier. As an object's speed climbs closer to light speed, the energy required to push it even a little bit faster does not increase steadily. It increases explosively, curving upward faster and faster, demanding disproportionately more energy for every additional sliver of speed gained. Engineers call this a runaway curve, the kind of graph that looks perfectly ordinary at first glance and then suddenly shoots almost straight upward, leaving the page entirely. Picture filling a swimming pool with a garden hose. For the first half of the pool, progress feels steady and predictable. As the water level climbs toward the very top edge, though, imagine the pool somehow needing exponentially more water for every additional inch, until filling that last fraction of an inch alone would require an ocean's worth of water. That escalating, punishing cost is exactly how energy behaves as a spacecraft's speed approaches light speed. This single fact reshapes the entire conversation about interstellar propulsion, moving it well past the simple question of building bigger engines or gathering more fuel explored in earlier chapters with chemical rockets and fusion reactors. Even with a perfect, loss-free engine, converting 100% of its fuel directly into thrust with no waste whatsoever, the raw energy requirement for reaching a meaningful fraction of light speed remains almost incomprehensibly large, on the same scale as the total energy our sun radiates into space every few seconds. Realistically, most serious interstellar spacecraft concepts, including the fusion-powered Daedalus design covered earlier, top out somewhere between 10 and 20% of light speed. Engineering ambition has little to do with that ceiling. The energy wall itself sets the limit, growing steeper and steeper the closer a ship tries to approach the true, unreachable edge of light speed itself. Accepting this limit changes what an interstellar mission has to look like in practice. Ships will very likely cruise at a modest fraction of light speed, somewhere in the range explored by Daedalus and similar designs, rather than the dramatic near-light speed voyages so often depicted on screen. Journeys will be measured in decades rather than years, even to our closest stellar neighbours, and any crew signing up for the mission would need to accept that reality fully before the engines ever ignite. And here is where a second, entirely different danger enters the story, one that has nothing to do with engines or fuel or energy at all. Once a spacecraft actually reaches a meaningful fraction of light speed and begins its long coast through interstellar space, it runs headfirst into an enemy that most people never think to worry about, something far smaller than aliens or black holes, and in its own way, far more relentless. Space has a reputation for being empty, a vast, silent nothing stretching between stars. That reputation is not quite accurate. Scattered throughout the seemingly empty gaps between star systems, drifts a thin, ghostly mixture of gas and dust known as the interstellar medium. Under ordinary circumstances, this material is so sparse it might as well not exist. Just a handful of atoms scattered across a space the size of a swimming pool. Ordinary circumstances, though, assume you're sitting still. A spacecraft racing through that same thin scattering of gas and dust at a significant fraction of light speed experiences something entirely different. From the ship's perspective, every one of those scattered atoms and dust grains suddenly appears to be rushing directly toward the hull, at close to light speed itself, transformed from a lazy scattering of particles into what amounts to a continuous high-energy bombardment. The interstellar medium consists mostly of hydrogen and helium, the simplest and lightest elements in the universe, making up close to 99% of its total mass, mixed with tiny traces of heavier material, including carbon, oxygen, and even iron, locked inside microscopic grains of dust smaller than a speck of pollen. Individually, none of this sounds particularly threatening. A single hydrogen atom colliding with a massive spacecraft should be about as dangerous as a single raindrop hitting a battleship. Velocity changes everything about that comparison. An object's destructive power in a collision does not simply add up with speed. It grows dramatically faster than that, following the same relativistic mathematics covered earlier in this story. At speeds approaching even 20% of light speed, individual atoms striking a spacecraft's hull carry kinetic energy wildly out of proportion to their microscopic size, delivering a punch closer to a speeding bullet than a gentle raindrop. Dust grains pose an even more serious threat than individual atoms, simply because they contain vastly more mass packed into an object still smaller than anything visible to the naked eye. A single dust grain, invisible without a microscope, striking a hull at relativistic speed carries enough concentrated energy to vaporize a small crater on impact, releasing that energy in a flash of heat and pressure, powerful enough to damage sensitive equipment or slowly erode the ship's outer shell. Multiply a single collision by the sheer duration of an interstellar voyage, years or decades spent constantly ploughing through this thin but relentless field of atoms and dust, and the cumulative damage becomes a serious engineering problem in its own right. Picture a constant, grinding erosion rather than the rare, dramatic asteroid strike so often shown in movies. Thousands upon thousands of microscopic impacts steadily wearing away at the leading edge of the spacecraft over the entire course of the journey, sandblasting the hull mile after relentless mile. Engineers studying this problem discovered something particularly unsettling once they ran the numbers carefully. It turns out the danger scales up dramatically with the size of individual dust grains, and even a single unlucky encounter with one slightly larger than usual particle, still far too small to see, could deliver enough destructive force to seriously damage or completely destroy a spacecraft in a single instant. That specific danger, the one grain of sand capable of ending an entire mission, deserves its own closer look. Picture a grain of sand, the tiniest one you can imagine, smaller than the width of a human hair. Now imagine that same speck of matter slamming into the hull of a spacecraft at nearly 1/5 the speed of light. Physicists studying the exact dangers facing high-speed interstellar probes have run this calculation for real, and the results are genuinely alarming. At those speeds, the physics of a collision shifts entirely away from ordinary intuition. A dust grain striking a spacecraft does not simply dent the surface the way a pebble might scratch a car window. The impact happens so violently and so quickly that the grain essentially detonates on contact, converting its kinetic energy almost instantly into an intense flash of heat, concentrated in an incredibly small area. Researchers studying this exact scenario calculated that a single dust grain wider than about 15 millionths of a meter, a size still far too small to see without a powerful microscope, carries enough energy at these speeds to completely destroy a small, lightweight spacecraft in one single impact. Even smaller grains, the ones too tiny to cause instant catastrophic destruction, still inflict damage with every single hit. Scientists studying this problem found that repeated impacts from microscopic dust particles gradually melt and erode the outer surface of a spacecraft's hull, carving out countless tiny craters and stripping away thin layers of protective material over the course of a long journey. Combined with damage from individual atoms in the surrounding gas, a ship travelling at a meaningful fraction of light speed for years on end could see its outer shielding worn down by a measurable fraction of an inch, layer by layer, long before it ever reaches its destination. Engineers proposing serious relativistic spacecraft designs, including some of the concepts behind the tiny probes envisioned by the breakthrough Starshot laser sail project, have suggested a handful of possible countermeasures, building a thick forward shield out of extremely durable, heat-resistant material, something like graphite or beryllium, positioned like a shovel plow at the very front of the ship, could absorb the brunt of these impacts before they reach anything critical. Some researchers have even proposed a stranger solution, firing lasers ahead of the spacecraft's flight path to vaporize larger dust grains before the ship ever reaches them, essentially clearing a path through the danger before arriving. None of these solutions completely erases the risk. They reduce it, spread it out, buy the spacecraft more time and distance before critical damage accumulates, but the fundamental danger never fully disappears for a ship moving fast enough to make an interstellar crossing worthwhile within a human lifetime. Every single mile of the journey means more atoms, more dust, more accumulated wear against a hull that has to somehow survive it all, uninterrupted for years or decades on end. This is the quiet, grinding danger waiting in what looks, from Earth, like an empty and peaceful night sky. It is a slow, relentless siege carried out by matter so small it borders on invisible, and it represents only the first of the great physical threats facing anything brave enough, or foolish enough, to cross the gap between stars. Waiting just beyond it is an even more dangerous enemy, one that no amount of shielding has ever fully solved, an invisible storm of radiation capable of unraveling the human body itself, one cell at a time. Out here, past the last flicker of the Earth's protection, something invisible and relentless soaks straight through metal, through plastic, through flesh. Physicists call it space radiation, and unlike the dust and gas covered earlier, it cannot be dodged with a clever hull shape or a thicker shield alone. It arrives from every direction, at every moment, for the entire length of a voyage that could last decades. On Earth, two enormous natural shields work quietly overhead, protecting every living thing without anyone noticing. The planet's thick atmosphere absorbs most dangerous particles before they ever reach the ground, and Earth's magnetic field bends the rest away like an invisible force field wrapped around the whole planet. Astronauts aboard the space station orbiting close to Earth still sit mostly inside that protective bubble, shielded from the worst of it. Leave that bubble behind, and everything changes. Once a spacecraft crosses beyond the reach of Earth's magnetic field, it enters open, unfiltered space, where high-energy particles fired from the sun and from distant exploded stars race through the emptiness at close-to-light speed. These particles do not politely bounce off a spacecraft's hull the way a bullet might glance off armour. They tear straight through, colliding with atoms inside the ship's walls, and often inside the human body itself, knocking electrons loose and shredding delicate strands of genetic material along the way. Some of these particles began their journey long before Earth's own oceans ever formed, flung outward by the violent death of a massive star somewhere across the galaxy, wandering silently through the void for millions of years before finally slamming into a spacecraft that happened to cross their path at exactly the wrong moment. There is no dodging a threat with a history that long and a reach that wide. Recent missions have measured this danger directly. A capsule launched around the moon without any crew aboard carried sensitive instruments specifically to record radiation levels during the flight. Even wrapped inside a heavily shielded spacecraft, the instruments recorded a steady drizzle of radiation far higher than anything experienced by astronauts living aboard the space station closer to home. Multiply that exposure across years rather than days, and the numbers climb into genuinely dangerous territory. This creates a particularly cruel problem for spacecraft designers. Every other hazard covered so far, distance, fuel, speed, even dust impacts, can at least be reduced with enough clever engineering and enough time spent solving the math. Radiation resists that same kind of clean solution. Thicker walls help somewhat, but adding enough shielding to fully block the most dangerous particles would add so much mass that the ship becomes too heavy to launch or accelerate in the first place, dragging every propulsion problem from earlier chapters right back into the conversation. Engineers studying this challenge have discovered something even more unsettling hiding underneath the basic problem. Space radiation is not one single, uniform threat that a single shielding strategy could handle. It actually comes in two distinct forms, born from two completely different sources, behaving in two completely different ways once they strike a spacecraft. One type can be blocked with enough mass. The other type barely notices mass is even there, and in certain situations, thick shielding can somehow make the danger worse instead of better. Picture two very different kinds of danger raining down on a spacecraft from opposite directions in the sky. The first comes from our own sun, in sudden, violent bursts called solar particle events. During periods of intense solar activity, the Sun hurls massive clouds of energetic protons outward into space, sometimes with barely any warning. A spacecraft caught in the direct path of one of these bursts could expose its crew to a dangerous dose of radiation within a matter of hours. The good news is that this type of radiation behaves in a fairly predictable way. Solar particles carry moderate energy, and thick enough shielding, layers of water, plastic, or specially designed materials packed around a crew's living quarters can absorb and block most of the danger. Mission planners can even watch the Sun's activity and time departures to avoid the most violent periods, the way a sailor might check the weather before setting out to sea. A crew could even retreat temporarily into a small, heavily shielded storm shelter built into the ship, riding out the worst hours of a violent burst before returning to normal quarters once the danger passes. The second type of radiation tells a much darker story. Called galactic cosmic rays, these particles do not come from our Sun at all. They originate from distant, catastrophic events across the galaxy, exploding stars and other extreme cosmic violence, and they arrive constantly, from every direction, at speeds so extreme that ordinary shielding barely slows them down. Unlike the softer particles from solar events, galactic cosmic rays include heavy, high-energy atomic nuclei that punch through metal and plastic, almost as if the shielding were not there at all, carrying so much energy that a single particle can leave a visible track of damage through a solid block of material. Here is the genuinely disturbing twist. When these ultra-energetic particles slam into a spacecraft's hull, they do not simply stop. They shatter atoms inside the shielding material itself, creating a spray of new, smaller particles called secondary radiation, a shower of additional dangerous fragments born from the very material meant to provide protection. In certain cases, adding more shielding mass can actually increase the number of these secondary particles reaching the crew, rather than reducing the overall danger, a bizarre situation where more armour makes things worse instead of better. This split personality of space radiation forces an uncomfortable choice onto spacecraft designers. Shield heavily against the sudden, dangerous bursts from solar particle events, and you gain real protection during those specific events. That same shielding does almost nothing against the endless, grinding background hum of galactic cosmic rays, and in some configurations might even amplify it. No single wall thickness, no single material choice, solves both problems simultaneously. Researchers have proposed alternative strategies, including active shielding that uses powerful magnetic fields to deflect incoming particles before they ever strike the hull, mimicking in miniature the same trick Earth's own magnetic field performs for the entire planet. Generating a magnetic field strong enough to meaningfully protect a spacecraft would demand enormous amounts of continuous power, adding yet another item to the already crowded list of engineering problems facing any real interstellar mission. And even if every shielding strategy available today were somehow combined and perfected, a crew still could not escape every consequence of years spent bathed in this invisible storm. Radiation exposure does not announce itself with a dramatic flash or a sudden alarm. It works quietly, cell by cell, over months and years, and the damage often reveals itself only long after the harm has already been done. For a crew committed to a voyage lasting decades, understanding exactly what that slow damage looks like matters just as much as understanding the physics behind it. Cancer sits at the top of nearly every list of radiation-related risks, and for good reason. Space radiation damages the delicate genetic instructions stored inside every cell, and while the human body has remarkable tools for repairing that kind of damage, repeated exposure over years increases the odds that some damaged cell slips through unnoticed and eventually grows out of control. Astronauts on relatively short missions already face measurably higher cancer risk than people who never leave Earth. Stretch that same exposure across a multi-year interstellar voyage, and the odds shift dramatically further in the wrong direction. Cancer is far from the only concern. researchers studying astronauts and laboratory animals have found that radiation exposure damages the tiny blood vessels feeding the heart, potentially accelerating cardiovascular disease years or decades before it would normally appear. It clouds the lens of the eye, leading to cataracts at a much younger age than typical. It even appears to interfere with the immune system, leaving the body less capable of fighting off ordinary infections during a mission where evacuation to a hospital simply does not exist as an option. Some researchers describe the overall pattern as a kind of accelerated aging, as though years of ordinary wear and tear on the body get compressed into a fraction of the normal time. Perhaps the most unsettling research involves the brain itself. Laboratory studies using radiation matched to deep space conditions have found measurable changes in a brain region called the hippocampus, an area deeply tied to memory formation and learning. Animals exposed to this kind of radiation show altered behaviour, slower learning, and disrupted memory function, effects that persist long after the original exposure ends. Some studies have even found lasting changes in how brain cells communicate with each other, changes that show up months after the original radiation exposure ended and never fully reverse. Applied to a human crew on a multi-year voyage, this raises a genuinely uncomfortable question. Could the very people responsible for keeping a starship running safely find their own judgment and memory quietly eroding along the way? None of this means interstellar travel is doomed before it begins. It does mean radiation cannot be treated as a background inconvenience, something engineers patch with a slightly thicker wall and move on from. It has to be treated as one of the central design challenges of the entire mission, woven into crew selection, ship architecture, mission length, and even the psychological support systems built into daily life aboard the ship. This grim tally of long-term damage makes one thing painfully clear. Humanity already possesses a shield capable of fully solving this problem, an enormous, elegant, incredibly effective one. It simply happens to be built into an entire planet, invisible, silent, and easy to take completely for granted until you imagine trying to build a smaller version of it yourself, floating in the void between the stars. Every single day, without asking for thanks, Earth performs an act of protection so massive in scale that most people never think about it at all. Deep inside the planet, molten iron churns and swirls, generating a colossal magnetic field that extends far out into space, wrapping the entire Earth in an invisible cocoon. This magnetic shield, called the magnetosphere, deflects the vast majority of dangerous charged particles long before they ever reach the ground, quietly saving every living thing on the planet from a radiation environment that would otherwise make surface life essentially impossible. Picture an enormous invisible umbrella stretched out to cover an entire world, constantly absorbing a storm that never stops falling. Without it, the fierce stream of particles constantly flowing outward from the sun would have stripped away Earth's atmosphere long ago. The same fate that appears to have befallen Mars, a planet that lost its own protective magnetic field billions of years in the past, and with it, most of its air. Mars stands today as a kind of natural warning sign, a cold, thin-skinned world that shows exactly what happens to a planet once its magnetic shield finally shuts off for good. A spacecraft heading toward another star has no such luxury. It carries no molten iron core, no planet-sized magnetic field, nothing built into its structure that naturally deflects the endless storm of particles bombarding it from every direction. Whatever protection a crew receives has to be engineered from scratch, built and powered entirely by human hands, a task roughly equivalent to recreating one of nature's grandest and most complex phenomena inside a machine barely large enough to hold a crew. Some engineers have proposed exactly that. Rather than relying purely on thick physical walls, these designs imagine generating an artificial magnetic field around the spacecraft itself, using powerful superconducting magnets to create a miniature ship-scale version of Earth's own protective shield. In theory, A strong enough magnetic bubble could deflect incoming charge particles away from the hull entirely, sidestepping the secondary radiation problem that plagues heavier physical shielding. Turning that theory into hardware, though, runs into serious obstacles. Generating a magnetic field powerful enough to meaningfully protect a spacecraft demands enormous continuous electrical power, precisely the kind of energy budget already stretched to its absolute limit by whatever exotic propulsion system is pushing the ship forward in the first place. The magnets themselves would need to operate at temperatures near absolute zero to function efficiently, adding an entire additional life support system dedicated purely to keeping shielding equipment cold enough to work, on top of everything already needed to keep the human crew alive. Even a partially successful artificial magnetosphere would mark a genuine engineering triumph, meaningfully reducing radiation exposure across a multi-year voyage. Achieving Earth's full, effortless level of protection, though, remains firmly out of reach for the foreseeable future. Another item on the long list of problems any interstellar mission has to survive rather than fully solve. And radiation is far from the only invisible danger facing a crew locked inside a metal hull for years on end. An entirely different kind of threat waits inside the ship itself, one with nothing to do with physics or particles at all, buried instead inside the delicate, easily disrupted balance of keeping human beings fed, watered, and breathing without a single resupply from Earth for the rest of their lives. Step aboard any spacecraft attempting a genuine interstellar voyage, and you step into something closer to a tiny sealed planet than a vehicle. Every breath the crew takes, every sip of water, every bite of food has to come from somewhere inside that sealed hull, recycled and regenerated endlessly for years or decades, without a single resupply mission ever arriving from Earth. Building a system capable of doing that reliably ranks among the hardest engineering challenges facing any interstellar mission, harder in some ways than the propulsion problem that gets far more attention. Humanity has actually attempted a real-world test of this exact idea, and the results offer a sobering preview of just how difficult sealed survival really is. In the early 1990s, a team of researchers sealed 8 people inside an enormous glass and steel structure in the Arizona desert, covering an area roughly the size of 2.5 football fields and built to mimic several different Earth ecosystems, complete with a tiny rainforest, a farm, a small ocean, and a desert, all designed to work together and sustain the people living inside for 2 full years without a single molecule of air or water crossing the sealed boundary. The experiment revealed almost immediately how fragile a fully closed system really is. Oxygen levels inside the structure began dropping steadily, month after month, as microorganisms living in the soil quietly consumed more oxygen than the plants inside could replace. Within about a year and a half, oxygen concentration had fallen so low that the air inside felt like standing on a mountain more than 2 miles high, leaving the crew constantly tired, foggy-headed, and struggling to think clearly. Engineers eventually had to pump in emergency oxygen from outside, breaking the whole point of the experiment just to keep everyone safely breathing. Oxygen was only part of the story. Nearly a third of the animal and plant species originally placed inside the sealed structure died out before the experiment even ended, including every single pollinating insect, which meant many food crops struggled to reproduce naturally. Meanwhile, cockroaches and ants, uninvited stowaways that arrived hidden in the original soil and plants, multiplied wildly with nothing left to keep their numbers in check. Feeding 8 people also proved dramatically harder than expected. Crops failed more often than planners anticipated, and the crew spent long hours each day simply working the fields, often going hungry despite that constant labour. Combined with the stress of watching their carefully built world slowly fall apart around them, the crew's relationships eventually frayed as well, splitting into opposing factions that stopped speaking cooperatively with each other for stretches of the mission, some members reportedly refusing to interact except when strictly necessary for survival. This single experiment, conducted on Earth's own surface with rescue only a phone call away, revealed just how easily a sealed ecosystem can spiral out of balance. A real interstellar mission would face every one of these same challenges, magnified by the complete absence of any outside help whatsoever, and stretched across a journey lasting potentially many decades rather than a mere 2 years. Understanding exactly how that spiral begins and how quickly it can spread reveals one of the most sobering lessons any future Starship designer will ever have to learn. A sealed ecosystem does not usually fail because of one giant dramatic disaster. It fails because of something small, almost boring, quietly going wrong in a system too interconnected to absorb the mistake. This is the lesson buried inside the Arizona desert experiment covered in the last chapter, and it carries enormous weight for anyone designing a ship meant to keep a crew alive for generations. Consider what actually happened when oxygen levels started falling inside that sealed structure. The root cause turned out to be something almost nobody had planned for carefully enough. Rich, organic soil, packed full of hungry microorganisms, had been used to help plants grow strong and healthy. Those same microorganisms consumed far more oxygen than anyone anticipated, quietly eating away at the breathable air, while everyone focused on more obvious concerns like growing enough crops. Nobody intended for the soil itself to become dangerous. It simply happened as a side effect of a decision that seemed perfectly reasonable at the time. This is precisely what makes closed ecosystems so treacherous compared to Earth's own gigantic, sprawling biosphere. On Earth, an enormous planet full of oceans, forests, deserts, and countless overlapping ecosystems provides staggering redundancy. If one region of forest struggles, countless others continue functioning normally, and the whole system barely notices the disruption. A sealed spacecraft habitat has none of that redundancy built in. Every system connects directly to every other system, with no backup planet waiting in reserve if something breaks. The die-off of pollinating insects inside the sealed experiment illustrates this same fragility perfectly. Losing every single pollinator might sound like a minor detail buried inside a long list of problems, but it directly threatened the crew's entire food supply, since many crops depend entirely on insects to reproduce successfully. One small, seemingly unrelated failure, insects struggling inside an unfamiliar sealed environment, rippled outward into an entirely different system, threatening the crew's ability to feed themselves at all. Meanwhile, cockroaches and ants that had hitched an uninvited ride inside the original soil found the sealed environment perfectly suited to their needs, multiplying wildly with nothing left to check their numbers once so many of their natural predators had already vanished. Now, imagine this same fragile chain of dependencies stretched across decades of travel through the emptiness between stars rather than 2 years, with rescue available nearby, with absolutely no possibility of outside intervention if something starts to go wrong. A single unexpected microorganism, a single insect population that fails to thrive, a single miscalculation in how much oxygen the soil will consume could set off a slow-motion crisis that takes years to fully reveal itself, by which point reversing the damage might already be impossible. Engineers studying this problem argue that any real generation ship would need staggering amounts of redundancy built directly into its design, multiple backup ecosystems, careful monitoring of every biological process, and crew members trained extensively in ecology alongside their other duties. Even then, no one can promise a sealed system stretched across decades would never suffer its own version of that Arizona desert crisis. And even if the ecosystem itself somehow holds together perfectly, an entirely different kind of strain waits quietly in the background, working directly on the minds of the people trapped inside that same unchanging metal world, rather than on plants and oxygen levels. Somewhere around month 4 of an experiment simulating a mission to Mars, a member of the isolated crew began showing signs of depression that would persist for most of the remaining confinement. He was not alone. Other participants developed disrupted sleep cycles, insomnia, and physical exhaustion that only grew worse as the months dragged on. This was a carefully designed simulation rather than a real spaceflight. 6 volunteers sealed inside a mock spacecraft on Earth for over 500 days, built specifically to study exactly what happens to the human mind when the walls never change and the horizon never shifts. Researchers running that study, along with similar experiments conducted inside isolated domes on remote volcanic landscapes, discovered a consistent and troubling pattern. Mood tends to decline steadily over time. Motivation fades. Small irritations between crew members, the kind easily brushed aside during a short mission, start accumulating into genuine, lasting conflict. Researchers also noticed crew members growing increasingly sedentary as the months dragged on, moving less, sleeping at odd and shifting hours, and slowly withdrawing from the same activities that had kept them engaged early in the mission. In one especially telling result, researchers found that just 2 stressed-out crew members accounted for the overwhelming majority of all conflicts recorded during the entire mission, suggesting that a single struggling person aboard a real starship could destabilize an entire crew's dynamic. Here is the deeply uncomfortable part. Even the longest of these simulated missions, stretching past a year and a half, represents only the tiniest fraction of what a genuine interstellar voyage would actually demand. A real mission to another star system would likely last decades rather than 500 days, an isolation experience so far beyond anything ever studied that researchers can only guess, based on these shorter simulations, at how severely the psychological toll might compound over that much longer stretch of time. Picture the actual sensory experience facing a real interstellar crew. No blue sky, no wind on your face, no fresh horizon to look toward and dream about reaching someday soon. Just the same metal corridors, the same faces, the same recycled air, day after day, year after year, for the majority of a human lifetime. Even astronauts aboard the International Space Station, protected by regular supply missions and the ability to gaze down at Earth from their windows, report significant psychological strain after missions lasting only a handful of months. Some researchers have proposed psychological countermeasures, structured mental health check-ins, virtual reality environments simulating open landscapes back on Earth, carefully designed daily routines meant to preserve a sense of purpose and progress throughout the long, unchanging voyage. These tools genuinely help during shorter missions. Whether they remain effective across an entire multi-decade journey, stretched across generations of crew members who never asked to be born aboard a moving spacecraft in the first place, remains an open and deeply uncertain question. This raises an entirely new kind of problem, one that has nothing to do with engines, radiation, or oxygen levels. If a single human lifetime cannot realistically endure the full length of an interstellar voyage without serious psychological strain, perhaps the mission itself needs to be redesigned around an entirely different structure altogether, one where no single person ever has to survive the whole journey alone. What if nobody aboard a starship ever had to survive the entire journey at all? This is the strange, quietly radical idea behind what scientists call a generation ship, a spacecraft built for an entire self-contained society rather than a single crew making a single voyage, a society born, raised, and eventually laid to rest, all without ever setting foot on solid ground. The concept traces back further than most people realise. Nearly a century ago, a pioneering rocket scientist wrote about the eventual need for what he called an interstellar ark, a vessel built to carry humanity itself across the vast gap between stars, since no engine imaginable at the time could cross that distance within a single human lifetime. Decades later, engineers sketched out detailed designs for enormous ships, some stretching longer than several football fields laid end to end, meant to house hundreds of people living, working, and raising children during a multi-generation crossing to another star system. Here is how the idea actually works in practice. The first generation to board the ship accepts a journey they will never personally complete, spending their entire adult lives travelling through empty space, raising children who are born already in transit. Those children grow up knowing nothing but the ship itself as home, eventually raising their own children in turn, who might finally step off the ship generations later onto a planet none of their ancestors ever personally saw with their own eyes. Somewhere in the middle of that long chain sits a generation who will live their entire lives, birth to death, without ever knowing Earth or their distant destination as anything more than a story passed down from people they never met. Researchers studying this concept seriously in recent years have launched design competitions inviting engineers and scientists worldwide to sketch out exactly what such a ship would need, imagining a journey lasting roughly 250 years, long enough for numerous full generations to be born and raised entirely aboard the vessel before arrival. The challenge extends far beyond simply building bigger engines or thicker radiation shielding. It demands designing an entire functioning society, one capable of preserving knowledge, maintaining mental health, and staying genuinely committed to a shared mission across generations who had absolutely no say in the decision that shaped their entire lives. This is where the idea starts raising questions that go beyond engineering entirely and edge into genuine ethical territory. Every child born aboard a generation ship inherits a life sentence they never agreed to, confined permanently to a metal world, tasked with continuing a mission chosen by ancestors they may never have even met. Supporters of the concept argue that humans have always been born into circumstances they did not choose, cultures, nations, and family responsibilities passed down without consent, and that a generation ship simply represents an extreme version of something already deeply woven into human history. Whether or not that argument satisfies every ethical concern, the practical challenges alone remain staggering. Keeping a closed ecosystem functioning, covered in earlier chapters, becomes dramatically harder when stretched across 2.5 centuries rather than mere years. And beneath even that challenge sits a problem so fundamental that entire teams of scientists have dedicated careers to solving it. Simply figuring out how many people you would actually need aboard that ship in the first place, just to keep the species itself healthy and viable by the time anyone finally arrives. Every popular movie and novel about generation ships tends to picture a cozy, manageable crew, maybe 100 people, perhaps a few hundred at most, living together in tight community aboard their floating world. Scientists who actually ran the numbers on this question discovered something the movies almost never get right. A crew that's small would be catastrophically, dangerously insufficient, dooming the entire mission to genetic collapse long before the ship ever reached its destination. The underlying problem traces back to basic biology. Every human population needs a wide enough pool of genetic variety to stay healthy across multiple generations. Shrink that pool too far, and close relatives start reproducing with each other more and more frequently, simply because the available options run out. This process, called inbreeding, gradually increases the odds of rare genetic diseases appearing, weakens the population's ability to resist disease, and can trigger a slow, compounding decline in overall health that gets progressively worse with each passing generation. Researchers modelling this exact scenario for a realistic multi-generation interstellar voyage found the results genuinely alarming. A starting population of only 150 people, roughly the size of crew often imagined in science fiction, would lose an enormous majority of its original genetic diversity within just 30 generations, a level of decline serious enough to threaten the long-term health and survival of everyone aboard. Even a crew several times that size, several hundred people, still fell dangerously short of what the mathematics demanded for a safe, multi-century voyage. So what number actually works? Detailed population modelling, accounting for accidents, disease outbreaks, and the ordinary randomness of who has children with whom suggests a genuinely viable generation ship would need somewhere between 10,000 and 40,000 people aboard from the very beginning, carefully balanced across different ages, backgrounds, and family lines, in order to preserve enough genetic diversity to remain healthy across a journey stretching many generations into the future. That number reshapes the entire conversation about what a real generation ship would actually need to look like. Picture an entire floating city rather than a single spacecraft carrying a tight-knit crew of a few dozen familiar faces, requiring exponentially more living space, exponentially more food production, exponentially more of every single life support system covered in earlier chapters, all scaled up by a factor of 100 or more compared to the small, cozy crews so often depicted on screen. Some researchers studying this problem have suggested an alternative approach entirely. Rather than cramming tens of thousands of people into one enormous single point of failure vessel, launch several smaller ships together instead, travelling close enough to trade resources and maintain genetic exchange between separate populations, but far enough apart that a single catastrophic accident aboard one ship would not doom the entire expedition at once. It is a clever solution to the genetics problem, though it multiplies every other engineering challenge covered so far by however many separate vessels the mission ultimately requires. Solving the genetics puzzle only opens the door to an entirely different kind of challenge. Tens of thousands of people, spanning multiple generations, confined together for 2.5 centuries, need something else entirely to survive that stretch of time without collapsing into chaos. They need some form of government, some system for making decisions, resolving disputes, and holding society together, with absolutely no way to walk away from their fellow citizens, ever, for the rest of their lives. Imagine living in a country you can never leave, surrounded by the exact same group of people for your entire life, with no border to cross, no new city to move to, and no possibility of starting over somewhere else if things go badly wrong. This is the political reality facing any generation ship, a floating nation with a population in the tens of thousands, expected to govern itself successfully for 2.5 centuries without a single outside authority to step in and help. Ordinary nations on Earth, however troubled, still benefit from something a generation ship completely lacks. People can emigrate. New ideas and new populations can arrive from outside. Trade and communication with other nations offer pressure valves that release built-up social tension before it boils over into crisis. A generation ship enjoys none of these safety mechanisms. Every conflict, every disagreement, every power struggle has to be resolved entirely from within, among the same closed group of people, generation after generation, with genuinely nowhere else for anyone to go. Even the harshest, most isolated settlements ever built on Earth could still, in theory, send someone walking toward the horizon in search of a different life. A generation ship offers no horizon to walk toward at all. Researchers studying this problem point to a particularly tricky challenge buried inside the mission's own timeline. The people who originally agreed to the journey, who understood and accepted its risks and sacrifices, will not be the people who eventually complete it. Their children, grandchildren, and great-grandchildren inherit both the mission and the obligation to keep pursuing it, without ever having personally chosen it themselves. Maintaining genuine commitment to a centuries-long goal across that many generations, especially once the excitement and idealism of the original launch fades into ancient history, represents one of the least understood challenges in the entire field. Historical experience with isolated human communities on Earth offers a few sobering hints about what could go wrong. Small, cut-off populations sometimes develop rigid, controlling social structures specifically to maintain order and enforce cooperation, since the normal pressures that check bad leadership in open societies, elections, free movement, outside scrutiny, simply do not exist in a sealed environment. Other times, isolated communities fracture into competing factions, exactly the kind of social breakdown already observed during the much shorter closed ecosystem experiment covered several chapters earlier, when a crew of only 8 people split into opposing groups after less than 2 years of confinement. Some researchers designing generation ship concepts have proposed elaborate governmental structures specifically built to survive this challenge. Systems with built-in checks on any single leader's power, mandatory education programs designed to keep the original mission's purpose alive across generations, and carefully designed social structures meant to prevent the kind of runaway conflict that could tear a closed, inescapable community apart from within. Whether any system, however carefully designed on paper, could genuinely hold together for 2.5 centuries of real human behaviour remains one of the great unanswered questions hovering over the entire generation ship concept. Faced with a challenge this daunting, purely social and political, rather than mechanical or physical, some scientists began asking a fundamentally different question. What if you could avoid the multi-generational society problem altogether by making the entire crew experience the journey completely differently, instead of simply travelling faster, sidestepping both the genetics problem and the governance problem in one single radical stroke? What if a crew could simply sleep through the centuries instead of living through them? This idea, once purely the stuff of science fiction, has quietly become the subject of serious funded research by space agencies studying how to make long-duration spaceflight survivable, and the results so far are more promising and more strange than most people realise. The scientific term for this state is torpor, a deliberately induced deep sleep accompanied by a dramatic drop in body temperature and metabolic rate. Unlike ordinary sleep, torpor essentially puts the body into a kind of low power mode, dramatically reducing how much oxygen, food and water a person needs to survive during that period. A crew held in torpor for most of an interstellar voyage would require far less food, far less living space, and far less psychological support than a fully conscious crew, enduring decades of unchanging isolation, directly solving several of the problems covered in earlier chapters all at once. Researchers working on this technology, funded through a space agency program specifically designed to explore ambitious, far future concepts, have already demonstrated the ability to safely lower a person's core body temperature and induce a sleep-like state lasting up to roughly 2 weeks, using medical techniques originally developed to protect critically injured patients during emergency surgery. The body's metabolism slows measurably with every degree of cooling, meaning a person held at a lower temperature genuinely does burn through resources at a fraction of their normal waking rate. 2 weeks, of course, sits nowhere close to the years or decades a real interstellar voyage would require. Researchers studying this technology openly acknowledge that pushing torpor safely from weeks into months, and eventually toward years, remains a serious unsolved medical challenge. The human body was never designed to remain in a state of drastically reduced activity for that length of time, and doctors still do not fully understand every risk involved in attempting it, from muscle loss and bone density decline to unknown long-term effects on the brain itself. There is also the psychological benefit hiding inside this idea, easy to overlook amid all the medical details. A crew that spends most of the journey asleep never experiences the crushing monotony of unchanging metal corridors covered in the earlier chapter on psychological strain. They close their eyes near Earth and open them again, from their own subjective experience, remarkably close to their destination, skipping over the isolation entirely rather than enduring every single day of it. Engineers designing torpor-based spacecraft have already sketched out habitat concepts built specifically around this idea. Smaller, lighter structures than a fully active generation ship would ever need, since they no longer require decades of continuous food production, recreational space, or full-scale social infrastructure. Instead, the crew would cycle in and out of torpor periodically, waking briefly for essential maintenance and monitoring before returning to their extended, artificially induced rest. If humans could truly master this technique, the inspiration for how to actually pull it off might come from a surprisingly unglamorous source, one that has been perfecting deep, extended dormancy for millions of years without any laboratory equipment whatsoever. Somewhere in the forests and mountains of Earth, an ordinary animal already knows exactly how to survive months of reduced activity, and engineers studying human hibernation have started paying very close attention to how it manages the trick. Every winter, in dens scattered across forests and mountainsides, an ordinary-looking animal performs a feat of biological engineering that puts humanity's best torpor research to shame. Bears enter a deep, extended state of reduced activity lasting months at a time, and remarkably, they emerge from it healthy, strong, and largely undamaged by an experience that would devastate almost any other large mammal, humans very much included. Scientists studying bear physiology have discovered some genuinely strange tricks hiding inside this process. A hibernating bear's internal body temperature drops only slightly, nowhere near as dramatically as smaller hibernating animals like ground squirrels, yet its metabolism still slows down substantially, dropping its overall energy use to a small fraction of normal levels. Its heart rate falls to a slow, steady crawl. Perhaps strangest of all, a hibernating bear does not urinate at all during the entire winter, instead recycling waste nitrogen back into usable protein, a biological trick that helps prevent the muscle wasting typically seen whenever an animal, or a human, spends extended time completely inactive. This last detail fascinates researchers working on human torpor more than almost anything else. One of the biggest obstacles facing any long-duration human stasis technique involves exactly this problem: severe muscle and bone loss during extended inactivity. The same issue already documented among astronauts spending months aboard the space station in weightlessness. Even with rigorous daily exercise routines, astronauts still return to Earth with measurably weaker bones and muscles, a problem that would only grow worse across a torpor state lasting years rather than months. If engineers could somehow replicate even a fraction of the biological trick bears use to recycle nitrogen and preserve muscle tissue during their long winter sleep, it could solve one of the most stubborn medical hurdles standing between short-term medical hibernation and genuine multi-year human stasis. Bears offer another valuable lesson buried in how gently they enter and exit hibernation. Unlike the abrupt, medically induced cooling techniques currently used in human torpor research, a bear's body transitions gradually into its winter state over the course of days, adjusting numerous biological systems in careful, coordinated sequence. Researchers studying this natural process hope that mimicking its gradual multi-system approach, rather than forcing rapid changes all at once, might make extended human torpor considerably safer and more sustainable than current techniques allow. None of this means scientists have cracked the code of human hibernation simply by studying bears closely enough. Human physiology differs from bear physiology in countless important ways, and no researcher seriously expects people to someday hibernate exactly like a grizzly curling up in its den. What bears offer instead is proof, walking, breathing, thoroughly convincing proof that extended, safe, low-damage dormancy across months of time is not some fundamental biological impossibility. Evolution has already solved a version of this exact problem, refined across millions of years, sitting quietly in dens across the planet, waiting for curious scientists to study it closely enough to borrow its secrets. If sleeping through the journey still cannot stretch far enough to cover a true multi-century voyage, some researchers have proposed skipping the adult human traveller altogether, sending instead something far smaller, far lighter, and in its own strange way, even more radical than a crew locked in torpor for years on end. What if the crew of a starship never grew up on Earth at all, and instead began their entire existence already in transit, floating between the stars from the very earliest moments of biological life? This unsettling but genuinely serious proposal involves sending a carefully preserved collection of frozen human embryos rather than a crew of living, breathing adults, tucked inside a spacecraft dramatically smaller and lighter than anything required to keep a full-grown crew alive for decades. The appeal of this approach lies almost entirely in weight. Every challenge covered throughout this entire story so far, fuel requirements, radiation shielding, food production, psychological support, scales directly with how many living, breathing people a spacecraft needs to keep alive during the journey itself. Remove the living crew from that equation entirely, replacing them with tiny frozen embryos requiring only careful temperature control rather than food, air, or entertainment, and the entire mass and complexity of the mission shrinks dramatically. Scientists studying this concept envision a spacecraft carrying a genetically diverse collection of frozen embryos, along with sophisticated robotic systems capable of thawing, growing, and eventually raising the very first generation of human children upon arrival at a distant star system, all without a single adult human ever making the actual journey. The robotic systems themselves would need to handle everything a human parent normally provides: nutrition, medical care, and even education, essentially building an entire artificial nursery and childhood from scratch, light years from the nearest human civilization. Serious obstacles stand in the way of this idea working in practice, some of them surprisingly fundamental. Freezing living human embryos for extremely long durations remains technically difficult, since ice crystals forming during the freezing process can damage delicate cell structures beyond repair. Researchers have made real progress using specialized freezing techniques that avoid forming damaging ice crystals in the first place, though preserving embryos successfully across a journey lasting centuries, rather than the years currently demonstrated in fertility clinics, remains entirely unproven. There is an even larger obstacle waiting after the freezing problem gets solved. No robotic system currently exists that can fully replace the incredibly complex biological process of pregnancy and early childhood development. Scientists have made genuine progress building experimental systems capable of supporting extremely premature animals outside a biological womb for limited periods, promising research that could eventually mature into something resembling an artificial womb. Scaling that technology up to reliably grow and raise entire human generations from frozen embryos without a single human caregiver present for guidance remains firmly in the realm of future speculation rather than demonstrated engineering. The philosophical weight of this proposal runs just as deep as its technical challenges. The first humans to ever set foot on a planet around another star would have no living parents, no direct memory of Earth, and no personal connection to the civilization that sent them, raised entirely by machines executing instructions programmed centuries earlier by people long since dead. Whether that qualifies as a triumphant solution to interstellar travel, or something considerably stranger and more unsettling, depends entirely on how comfortable you are with the idea in the first place. Every proposal covered so far, whether a full crew, a sleeping crew, or a shipment of frozen embryos, shares one final, unavoidable requirement in common. Something has to keep the spacecraft itself running, intact, and functional for the entire multi-decade or multi-century journey, long after the engineers who originally built it have grown old and died back on Earth. No matter which crew arrangement a mission eventually chooses, whether a full generation ship, a sleeping crew, or a shipment of frozen embryos, one problem remains stubbornly identical across every version of the plan. The spacecraft itself has to keep functioning flawlessly for decades or centuries without a single repair shop, spare parts warehouse, or emergency rescue mission anywhere within reach. On Earth, machines break down constantly, and humans fix them constantly, calling in specialists, ordering replacement parts, and troubleshooting problems using decades of accumulated repair experience. A starship crossing interstellar space enjoys none of that support network. Picture trying to keep a car running for 2 centuries straight, through every kind of weather, without ever once visiting a mechanic or ordering a replacement part from a factory. Every single component, from life support systems to propulsion hardware to the ship's own structural hull, has to either last the entire journey without failing, or the ship needs some built-in way of repairing and replacing that component entirely on its own, using only whatever materials and tools happen to be stored aboard. This challenge grows even more serious the longer a mission stretches. A ship designed for a 50-year flyby mission, similar to the fusion-powered Daedalus concept covered earlier, faces a genuinely difficult but at least somewhat bounded engineering problem. A generation ship carrying passengers for 2.5 centuries faces something closer to an impossible one, since virtually every mechanical and electronic system humans currently build tends to wear out, corrode, or become technologically obsolete within a small fraction of that timeline. Engineers studying this problem have proposed increasingly ambitious solutions. Some designs call for massive redundancy, building multiple backup versions of every critical system, so that individual failures never threaten the entire mission. Others propose onboard manufacturing facilities, essentially flying factories capable of producing replacement parts from raw materials carried aboard the ship, allowing the crew to repair almost anything rather than relying on a fixed supply of spares that could eventually run out. The most radical proposals borrow directly from an idea developed decades ago by a brilliant mathematician studying the theoretical limits of self-reproducing machines. Imagine a spacecraft, or a fleet of smaller robotic helpers travelling alongside the main ship, capable of mining raw materials from asteroids or other bodies encountered along the way, and using those materials to manufacture entirely new components, or even entirely new copies of themselves, extending the mission's lifespan indefinitely without ever needing to return to Earth for anything at all. Building a machine genuinely capable of this kind of independent, self-sustaining repair and reproduction remains far beyond current technology, requiring levels of artificial intelligence, robotic dexterity, and materials processing that engineers are only beginning to explore even for far simpler applications closer to home. Yet the underlying logic remains compelling. A ship capable of repairing and rebuilding itself indefinitely could theoretically survive a journey of any length, sidestepping the entire aging and obsolescence problem that would otherwise doom any fixed, unchanging spacecraft launched centuries before its own arrival. Faced with this staggering pile of unsolved problems, radiation, genetics, governance, mechanical survival, some researchers have proposed the most radical solution of all, one that does not try to solve the problem of keeping fragile human bodies alive across the stars, but instead asks whether those bodies need to make the journey in the first place. What if the traveller who eventually steps onto a planet around another star never had a body to begin with, at least not the same body that once lived and breathed on Earth? This is the strange, genuinely serious proposal at the far edge of interstellar mission planning, an idea that sounds like pure science fiction until you notice how many real scientists take it seriously as a practical engineering solution rather than a philosophical thought experiment. The concept, often called whole brain emulation or mind uploading, imagines scanning a human brain in staggering detail, capturing the precise pattern of connections between billions of neurons, and then recreating that exact pattern inside a sufficiently powerful computer. If consciousness and memory genuinely emerge from the physical structure and activity of the brain, as most neuroscientists currently believe, then a sufficiently accurate digital copy of that structure could, in theory, think, remember, and experience the world in essentially the same way the original biological brain once did. Applied to interstellar travel, this idea solves an enormous number of problems covered throughout this entire story in one dramatic stroke. A digital mind requires no food, no water, no breathable air, no radiation shielding thick enough to protect fragile biological cells, and no elaborate psychological support system to survive years of unchanging isolation. The entire mass of a human traveller could shrink from an enormous life support dependent body down to something closer to a small, durable data storage device, dramatically easing nearly every propulsion and mass problem explored earlier in this story, including the crushing mass limitations that make laser sail concepts like Breakthrough Starshot completely impractical for carrying an ordinary human crew. Some researchers studying this idea imagine a scenario where the actual interstellar vessel remains tiny and impossibly light, similar in spirit to the smartphone-sized probes discussed several chapters back, carrying nothing but digital minds and detailed technical knowledge rather than living human bodies at all. Upon arrival at a distant star system, those digital minds could theoretically be transferred into robotic bodies, or perhaps eventually into newly grown biological ones, allowing the crew to experience their destination directly, rather than remaining forever trapped as pure information. Enormous obstacles stand between this idea and anything resembling reality. Nobody currently possesses the technology to scan a living human brain with anywhere near the precision required to capture its full complexity, let alone the computing power needed to simulate billions of neurons and their countless connections in real time. Deeper philosophical questions linger underneath the technical ones as well. Even if a perfect digital copy of your brain someday exists and thinks exactly as you would, deep uncertainty remains about whether that copy would genuinely continue your own personal experience, or whether it would simply be a new, separate mind that merely believes itself to be you. Whether or not humanity ever solves the philosophical puzzle at the heart of mind uploading, the concept illustrates something important about the entire search for interstellar travel solutions covered throughout this story. Nearly every serious proposal, from fusion starships to frozen embryos to digital minds, ultimately circles back to the exact same core challenge: reducing mass, extending survival time, and somehow closing the impossibly vast gap between what current technology can achieve and what reaching another star actually demands. 17 chapters ago, this story began with a single brutal number: a gap between stars so vast that our fastest spacecraft would need tens of thousands of years just to cross it. Remember that beach ball standing in for our entire sun, with the nearest star sitting an entire country's width away? Everything covered since then has been an attempt to answer one deceptively simple question: could a spaceship actually survive long enough to close that gap and arrive somewhere on the other side carrying anything resembling humanity along with it? The honest answer sits somewhere between an outright yes and a full surrender to impossibility, closer to a genuinely hopeful maybe than either extreme. Physics itself does not forbid the journey. Nothing covered throughout this entire story breaks any law of nature. Fusion engines like the Daedalus design could theoretically reach roughly 12% of light speed using technology humans already understand in principle, if not yet in practice. Time dilation genuinely would ease the subjective burden on any crew travelling fast enough. Radiation, however dangerous, can at least be partially managed with careful shielding and mission planning. Closed ecosystems, however fragile, can be engineered with enough redundancy and careful study of exactly how systems like Biosphere 2 originally failed. What the journey demands instead is scale, patience, and a willingness to solve problems that stretch across entire human lifetimes rather than single engineering projects. It demands mining infrastructure spread across an entire solar system just to gather enough fuel. It demands populations numbering in the tens of thousands, carefully managed across centuries to keep a crew's genetics healthy. It demands psychological and social systems robust enough to hold a closed, inescapable society together for generations who never personally chose their mission. It might ultimately demand solutions stranger than any single engineer working today can fully picture. Sleeping crews, frozen embryos, or digital minds detached from biology altogether. No single breakthrough solves the whole puzzle at once. Every chapter of this story represents its own separate mountain to climb, and reaching another star means climbing every single one of them, in sequence, without skipping a single step along the way. Perhaps the most important lesson buried inside this entire journey is not really about spaceships at all. It is about scale, and about how differently the universe behaves once you step outside the comfortable, familiar bubble of a single solar system. Every problem explored across these 33 chapters — fuel, physics, radiation, ecology, psychology, genetics, governance, mechanical survival — exists precisely because the gap between stars refuses to shrink down to a size that feels manageable using humanity's current tools and current lifespans. And yet, none of these obstacles arise from some fundamental law declaring the journey forever impossible. They arise from humanity still standing at the very beginning of a much longer story, one that started only a handful of generations ago with the first fragile rockets barely escaping Earth's atmosphere, and that could, given enough centuries of patient, determined progress, eventually stretch outward toward that same small red star sitting 4.2 light-years away, waiting quietly in the dark exactly where it has always been. So could a ship built by human hands someday actually survive long enough to reach another star? The evidence gathered across this entire journey suggests cautiously, remarkably, that the answer is yes, someday, if humanity chooses to keep building toward it, one impossible-sounding problem solved at a time.